Welcome back after the refreshments break. You're going to finish that later. Okay, now let's see our announcement video for our next lecture. Tobias Nyholm, imagine you're a traveling salesman about to visit 10 cities in Europe. You can visit them in any order, so what's the cheapest route? He will show us how to solve that with Dynamic Programming 101. Tobias, fire at will.
Thank you very much.
Thank you.
Yeah, so my talk is titled Dynamic Programming 101, which is, I'm gonna give you an introduction to dynamic programming. And I got some questions like, why do they say 101? And it's pretty much a reference to American colleges or American universities where they say 101 is the first class of the specific topics. So this is an introduction to dynamic programming. My name is Tobias Nyholm, and here's my Twitter handle. So if you want to harass me for the next 40 minutes, I can't really defend myself. I believe that web developers only cares about printing HTML really quickly. I wanna show you that it's more to programming than just printing stuff really quick. So that's why I gotta give this talk to show that there are some cool features except for echoing out HTML. Short about me first. I work at a company called Happer.com. I do some Symfony stuff, and I'm doing the PHP meetups groups in Stockholm, and I'm also doing plenty of open source. I started my I started my open source career in 2005 when PSR6 came out. So me and my friends thought like, hey, let's build adapters for Doctor and Cache in PSR6, and then we started to, why do we build adapters? So let's build actual implementations. So that's why we created PHP Cache. Shortly afterwards, I got interested in HTTP Plug, which is like an abstraction over HTTP clients. And when you do HTTP clients, you obviously do API clients and some mail clients. And I wrote a best practice document how you write API clients. And then I maintain Guzzle and Bus, and then I do some clients testing, geocoding, and plenty of other stuff. The project I'm interested most in is the NSA package. It totally violates all class privacy. So accessing private properties or methods, it's no issue with the NSA. It's great for testing and horrible for everything else. Let's get started. Say you got a problem, like an easy problem, how to get to work in the morning. So what you do is you start to try to put this problem into smaller tasks, like I should get dressed, I should make breakfast, and I should actually get to work with my car. And then you're breaking down these problem into even smaller tasks, and even smaller tasks, like which sweater should I wear, what trousers should I use, etc. So we do this with everyday tasks. We do this with every problem we got. And in if we got a problem like, hey, I want to build a website, you start thinking about, sure, we have design, we have some business logic, we have some models, and then you try to make these into smaller problems like, what are my data models? How should I store my entities, and etc. And this is called divide and conquer. And as developers, we pretty much know what it is about. We do this every day, and we do it automatically. And are you guys, when you see this, you might think of recursion. As a computer scientist, you might think of recursion, right? You have a big problem, you divide it into smaller things. And if you agree with me here, then everything is going to be smoothly from now on. If you don't know recursion, this is recursion. Say we want to have a function calculating factorial numbers. A factorial is, 3 factorial is 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. You all know factorials? Good. Here's an iterative function and a recursive function. So the idea of the recursive function is it has to call itself, and you have to kind of figure out that 4 factorial is actually 4 times 3 factorial. So this is what the recursion logic is on the bottom of the slide to the right. And there is a law in computer science that whenever you speak about recursion, you have to mention Fibonacci sequences. Fibonacci was a very old mathematician. He was living like 1,000 years ago, and he came up with a fun sequence of number. Fibonacci sequence was not invented by Leonardo da Vinci or the Da Vinci Code, as someone with confidence claimed that they were. Fibonacci sequence is something like this. Here is the first 17 Fibonacci numbers, and there is the index below it. And a Fibonacci sequence, the next Fibonacci number is the sum of the two previous Fibonacci numbers. So in code, this will look something like this. I figure out that Fibonacci for 5 is actually Fibonacci for 4 plus Fibonacci for 3. In math, it looks something like this. Very simple and straightforward. So if I ask you now, what is the 15th Fibonacci number? (610), first row, yes. I mean, I have some easy questions for you. This was an easy one. Oh, we redo this. What is the 15th Fibonacci number? Excellent, excellent. What if I asked you, though, the hard question? What is the Fibonacci number for 1002? It's a lot. It's actually a very, very large number, surprisingly large number. But what if I told you the Fibonacci number for 1,000 and Fibonacci for 1,001? So if I know these Fibonacci numbers, what is the Fibonacci number for 1,002? There's some, exactly. So if you know the result of some smaller problems, you can easily calculate the result for a larger problem, right? So if I give you x and y, what the actual values are, you could probably calculate this by hand. I want you to remember a lot of things, but I want you to remember that if you know the result of smaller problems, you can easily calculate the result of a large problem. Let's study the code again for Fibonacci. This is no surprise for anyone. Everybody understands this code. But as you can see, if you're calling fib5, there's a lot of calculations. So I call fib5, and as we see in the code, fib5 is 5 is not less or equal than 1, so we do an extra call to fib4 and fib3. And if we continue here, we have two additional calls. If we continue here, we see that those two additional calls generates even more calls and even more calls. So we can see we do a lot of computation here. We can also see that some computation is been doing unnecessarily. We calculate fib2 twice, thrice. We calculate fib2 3 times. So what if we kind of stored the result for fib2, or we cached the result for fib2? If we improved our function to something like this. This is the very same thing. I just slapped on a class here because it looks more nice. This is caching, or you may call it memorization if you're going to be very precise. I think I know some speaker this weekend. He said it was the difference between caching and memorization. Memorization is a proper name for it. Anyhow, same thing. I want to stress the main thing about dynamic programming is this. So you have a large problem, and you divide it into overlapping subproblems, and then you somehow reduce calculations. And this somehow could be by memorization. So if we study our algorithm again, or our call tree again, we had this, all the calls, and with adding the memorization or cache, we reduce it to this. And obviously, you can see that there's a large difference between how many calls we're doing. And this is just for fib5. Imagine fib500. We probably reduce like 99% of all of our calls. So with dynamic programming, you don't have to calculate everything. You're with me so far? Because we just done like the hello world of dynamic programming. This is the basics, this is the hello world. So let's consider the more fun stuff. And fun stuff is obviously graph theory. And I know that Christoph, he had a talk just earlier today about graph theory and the graph databases. I will not cover graph database so much, but this is graph theory. And the basics in graph theory, the first thing you need to know about graph theory is that these are not graphs. These are charts, these are diagrams, these are data visualization, images. You call them whatever, but these are not graphs. A graph has a node. A little bit more interesting graph has 2 nodes. And there's could be an edge between those nodes. This edge could either be undirected, you can go in any direction, or it can be directed. And an edge could also have a weight. So now you know basics of graph theory, and now you know basic of graph. No, you know basic of graph theory, and you know basic of dynamic programming. And so let's consider a little more fun graph, like this. This graph could represent like anything you like. It could be computers in a network. It could be people and if they know each other or not. Or it could be cities and the roads between the cities. And if we slap on some numbers here, it could be like how much data you can send between each computer, or how much the people like each other, or the actual distance between one city and the other. So let's consider the latter example. Let's consider their cities, and let's consider we want to find the shortest path between A and B. So we could, of course, with this small example, try to draw and figure it out, and doing whatever we like. But we could also be a little more systematic about it. So let's do a breadth-first search. Show of hands before now. How many of you are confident how a breadth-first search looks like? Okay, it's about 20%. Excellent, excellent. I'll explain it in detail. So what you're doing, the first step of the breadth-first search is you start with the start node, and then you're looking for all its neighbors in turn. So what I'm doing now, I'm looking for the first neighbor, and then I mark the cost of going there. Then I go for the second neighbor, and then the third neighbor. Feels pretty good so far. And now I'm going to the next unvisited neighbor, I mean the top one, and I'm looking at what its neighbors is. So I just continue. And also, now I'm starting with the node 3 now, and looking at its neighbors. And as you can see, I changed the number to a 5 from an 8, because I found a shorter path. And then I just continue this in an orderly manner until I found until I traversed my full graph, and then I can actually backtrack what's the shortest path really were. It might, I mean, like 80% of you have never seen this before, and I got some feedback in the previous talk I did saying, hey, let's show some code. I mean, we're programmers, we want to see code, not only images. So I'll show you code solving this graph. I removed the numbers because they only make things way more complicated than they should. The principle is the same. So this is a slightly easier example. And the code looks something like this. I decided to have a graph class, and then I have represent every edge in that graph. And I have a list of edges. The key of this list is basically a node, and then it has an array of the neighbors. And then I can easily add new links, and then my breadth-first search looks something like this. I just create a queue, which is the start node in it, and then I mark the start node as visited. Then I start my super long while loop, saying, while I have something in the queue, take the first element and look at all its neighbors, put the neighbors in the queue, and mark the neighbors as visited if I have not seen them before. I'll give you 30 seconds to look at this, because I know this is a lot of code to figure out if you haven't seen this before. That was the shortest 30 seconds you've ever seen. And when I'm done, when I've traversed the full graph, when I've traversed all the nodes, I'll just print the result. And as you can see down here, I printed backwards. You see how I was tricky when constructing my visited array? So the visited is actually a semi-linked list back. So I just printed backwards. And then, I just build up my graph down here. So when I run this, I'll get the BLHCA. And this, as you see, this is pretty much the shortest path if only calculate the number of nodes. I also do understand that pretty much it's 4 shortest paths in this graph. But you understand the principle. And say if I would have the weights here, I would do the same thing, but I also have to store the points of in my visited array. I have to store the cost to getting there, and I need to handle loops. But it works in the very same way. Are you happy with this? Because some of you are looking really confused right now, and that's not my intention, and it will get slightly worse. This is a matrix maze, and I hope that you can see that you can translate this to a graph. The number in each box is the cost to getting to this box. Do you see how you can translate this to a graph? Good. Or else you have to believe me, it's easy to translate to a graph. I choose this notation because I believe it will make more sense in a minute. The goal of this maze, you can move up, down, left, and right. And the goal of this is to navigate from the start to the goal. And if I slap on some colors here, it gets easier to see what the number really representing. So let's do the very same thing again. Let's do a breadth-first search here. So what I'm doing is I'm going by start node, and then I'm looking for all my neighbors. Then go for next neighbors, looking for all its neighbors. You know this by now, right? Now it plays by itself. So this actually trying to traverse the full graph until it traverses everything, and then it backtraces the shortest path, like we saw in code. I want to stress it searches the full map. You could do a breadth first, or you can also do a depth first. Like I said, breadth first is checking all its neighbors in turn, but a depth first is taking one neighbor and then you just walks down this path. And then it backs up a little bit, and then it walks down the next path. So they both search the full graph, and they both are assured to find the shortest path. But depending on your use case, one might have an average faster performance than the other. But what if we feel like, hey, what if we don't want to search the full graph? Couldn't we be a little more smarter? Maybe we use a greedy algorithm. So for every possible moment, we just take the best possible decision. That seems like a good idea, right? It actually is kind of a good idea. Not in this case, as you may have seen. So I take the best decision, and I found the one. That's awesome. Take another best decision, another one, and now I'm pretty much stuck in the wall of 8s here because of my best decisions. So in this particular graph, this is not the optimal algorithm. However, it's pretty quick because it doesn't search the full graph. But then again, I'm not guaranteed to get the optimal path. As a contrast to the best fit algorithm, I can do a worst fit algorithm. So at every possible moment, I take the worst possible decision, which actually, this sounds horrible compared to best fit, but they actually perform equally well on the random graph. And you can also do a random walk, so you just walk around randomly in the graph until you find your goal. And you obviously have to handle loops somehow, but these 3 algorithms, they perform equally well, and depending on your use case, you may pick one or the other, because on your specific use case, worst fit might be better. What I want to show here is these 3, best fit, worst fit, and random, they do not guarantee the optimal path, but they are very quick because they do not search the full graph. So what if we introduce some of our newly found dynamic programming knowledge to this? I want to introduce you Dijkstra's algorithm for finding the shortest path. Dijkstra's algorithm is fairly popular. Okay, it's super popular. So you might have heard of this, even though we haven't heard of breadth first yet. Anyhow, Dijkstra's algorithm is it's not too complicated to implement, but it's quite complicated to describe, so I'll better show you. So the first thing you do, you start with the start, and then you add on the number, how much does it cost to get here? What is the total cost of getting here? And that's 3. And then you're looking for all its neighbors and adding the costs. And now you select, and now I marked number 3, the start node, as visited. So now I'm looking for I'm looking for the discovered node that I have not yet visited, but with the lowest value. So something I haven't processed yet with the lowest value. So this is the top left one, and I'm discovering all its neighbors. And now, when I'm done, I'm looking for the node that I have discovered but not visited with the lowest value, and that's the number 2 box there. And I'm doing the same thing. And did you see there? I was pretty quick. Instead of adding a 7 here, I know that this is already, I will find a cheaper way to get in this node. So I don't modify this, I remove this link. And then I just continue with the next, the node that I have not yet visited, but have discovered and has the lowest value. And I'm gonna click a few more times until it plays by itself. So when you see it playing out, it doesn't look super complicated. Dijkstra's algorithm actually guarantees to find the optimal route, or the shortest path, or the cheapest path, or whatever. However, it does not search the full graph. This is the idea with dynamic programming again. I'll let it play out because you're way focused on this. It plays out whenever it's gonna go with the goal node there, then it knows it finds everything. So now I can backtrack this and find the shortest path. And as you may or may not see, there are some nodes here that I have not visited yet. I haven't not even discovered these nodes. And imagine a larger graph and not as weird a graph as I implemented. It may be a huge portion of nodes that you don't really see, but you still can guarantee that you found the shortest path or optimal route. So let's do the same thing again, but in a slightly different notation. I'm still looking at the start node, and I'm marking the distance. Then I'm discovering all my other nodes, looking at the difference, and looking at the distance or the cost. And from here, I'm starting 3 new Dijkstras. Dramatic pause. I'm starting 3 new Dijkstras and adding on a constant. And obviously, you see, solving a Dijkstras of 30, that's a hard problem. And now I'm starting solving 3 Dijkstras of 29. That must be an easier problem. And if I continue this, the same way I did before, now I have a Dijkstras of 27. And obviously, Dijkstras of 27 nodes gotta be easier than solving Dijkstras of 30. And I can store, these 3 Dijkstras could work together to save the number of calculations. But this is how I have a large problem, and solving the large problem by solving a smaller problem and adding on a constant. Pretty much like we did in Fibonacci. Last time I did this talk, people were like, wow, at this moment, but you're fine anyways. No worries. Thank you. Anyhow, if we're going to express this in more math, you may like this notation. So if you have a graph of n nodes, we know that the optimal solution is the same as the optimal solution for n minus 1 node plus n, or the optimal solution for n minus 1 nodes plus nothing. So either this node is in the optimal solution or not. That's basically what we're saying. So another way of picturing this is if we have A to F nodes, we know the optimal solution includes the optimal solution for B to F nodes and plus A, or maybe plus A, either plus A or not plus A. So we have a large problem, and we're solving this by solving a smaller problem and just adding a constant or whatever. With me so far? I'm gonna go even further now. This is way more math. Say we can assume in the graph here, we can assume there is an optimal path between I and j. And if we assume that the node before j, like k, we can calculate the optimal path between I and j by calculating the optimal path from I to k plus j. Thank you. Thank you very much. I know there's quite a numbers and math and theory here right now, so I want to take a pause and let you breathe or take a quick moment of processing what I just said. And I will tell you the hardest possible way to win $1 million. First, I will tell you about time complexity and the big O notation. Some of you might know this is the way to measure the effectiveness of algorithms. So the 4 algorithms I'm talked about is these 4. And as you can see, the first 3 have linear time complexity, which means that if I increased the number of nodes, if I double the number of nodes, I will double the amount of time running the algorithm. Dijkstra's algorithm, however, looks like it's a little bit worse, and it is worse in worst case. It says n log n. But Dijkstra's is way better on average. That's why it's faster, and that's why it's more used. A slightly different problem. I mean, I'm only looking at problems find the shortest path, which is quite easy problem, right? So what if we're looking at the problem that find the shortest path between a number of cities and then get back home, like the traveling salesman problem? I gotta visit these 5 cities, and I want to have the cheapest flight route around them. And this is a super hard problem, and the best algorithm we got for that is Bellman-Held-Karp algorithm, and has n to the power of 2 times 2 to the power of n time complexity. And if you don't know, if you can't really visualize how horrible time complexity that is, I've written a graph for you. I've written a diagram for you. Very scientific diagram showing time complexity. So, you've seen this before, right? I don't have to explain this in depth. There is a theorem saying that problems that you can only solve with algorithms with exponential or factorial time complexity, they are up there, and they're called NP. Problems you can solve within reasonable fast algorithms, they are called P. And if you want to win $1 million, you basically have to prove that these are separate groups of problems, or if there's the same group of problems. We don't really know. We think they're separate, but we don't really know yet. So what I'm basically saying is, if you take a problem in NP, like the traveling salesman problem, and you find a quick solution for that one, you're rich. Let's investigate the traveling salesman problem a little bit. I mean, we might consider that that's just an edge case of Dijkstra's, because Dijkstra's is finding the shortest path. But what if we want to find the shortest path visiting all the nodes, pretty much? So, yeah, it's Dijkstra's. It's traveling salesman a edge case of Dijkstra's, and not really, because Dijkstra's is finding the optimal path, not using all the routes necessarily. So what if we force Dijkstra's to use n number of nodes? And that's a good idea, but you could still have duplicates, right? So what if we're trying to remove duplicates and force a fixed path, a fixed length of the path? Could we solve TSP with Dijkstra's? And we're very, very close now, but we really can't. And I'll try to explain this with this image. So you recognize this? Dijkstra's is finding the shortest path from I to j by considering the shortest path from I to k plus j. So if Dijkstra's find the shortest path from I to k with no duplicates and with the fixed length, that's fine. But then when we add j, that might introduce a duplicate, because j might be in the shortest path from I to k. So sadly, it does not really work. And it's super close, but this Dijkstra edge case does not find the optimal path. If we wanted to modify Dijkstra somehow to find the shortest path, we need to remember not only the destination. We have to remember. Currently Dijkstra's, we remember how we got to k. We remember the node before it. But if we're going to solve TSP, we also have to remember all the steps how we get to k, all the intermediate nodes. And that sadly increased time complexity. This is a Bumblebee. Don't misuse it. This is a Bumblebee. It weighs about 1/10 of a gram. As you know, a bumblebee lives in a hive, and then it flies around to all the flowers, A, B, C, and D, to collect pollen or nectar or whatever. And it always finds the shortest path between the flowers and then get home. Even if we move a flower, it recognizes that we move the flower and it recalculates the shortest path. And the next day, it's just do the shortest path. So what I'm basically saying is the bumblebee solves TSP. Yeah. I'm also wondering, is the bumblebee smarter than a supercomputer? You may wonder why we spend so much time on TSP. I mean, it's not just me, everybody's doing TSP. And also, if you think about a hard problem, you'll probably raise your hand and say TSP, right? So we're spending so much time on this because it's a really easy problem to understand, but it's a really hard problem to compute. And I'll tell you that there is a way to convert a NP problem to another NP problem. So what I'm saying is, if you find a solution for one NP problem, you have a solution for all NP problems. And there is one NP problem called integer factorization problem, which basically means it's hard to factorize integers. And if you studied some security protocols, you will see that most security protocols starts with selecting two very large primes, very private and very secret primes, and then you multiply them together, and that's your public key. Because integer factorization is so hard, we know that even though we have the product of this multiplication, you will never find our secret primes. So again, what I'm saying is, if you solve the TSP, if you can efficiently solve TSP, you can efficiently also brute force all our society's encryption. And you can also solve cancer and cure cancer. And that's actually not a lie. Anyhow. You know Composer. Composer is also dealing with a NP hard problem. It's called the satisfactory problem, which basically it's trying to figure out what versions to download to your computer. So that's one reason why you feel Composer might be slow. Also network I/O. So whenever I'm faced with a really, really hard problem, I guess I want to try it, right? That's I don't try it because I think I can solve it. I just try to see what is my solution. So when I first heard of this problem, I tried to solve it. And what I did, I was pretty naive, or I am pretty naive. So I look at a simple TSP problem. This is the bee in the beehive again. And now I'm going to calculate one shortest path. So I have 5 nodes to select from, which just starts. So I chose H, because that's the hive. Now I have 4 options to choose next. I go with the B. Now I have 3 options. Now I have 2 options, 1 option, and now I found one path. Right? And as you may notice, I have 5, 4, 3, 2, 1 options, which you could realize that this algorithm of mine had to try 5 factorial options to make sure I find the optimal route. Okay? And 5 factorial is 120. And to get a sense of how quickly factorial grows, 15 factorial is 1.3 trillion. So with this algorithm, on my computer, I could maybe solve TSP of 25, 30, if I ran it a full day. And 30, that's not, I mean, we have more cities in Sweden than 30, so we can't really, it's not really useful for anything. So what if I, n factorial, so what if I applied my newfound dynamic programming skills here? So we know it's easier to calculate the full problem if you know the result of the subproblems. So I start calculating subproblems. I'll calculate this subproblem, find the optimal route here. I calculate this subproblem, a few other subproblems. And when I calculate these, I'll get to, and then I could easily build up a full result. And I will do this. This is the Bellman-Held-Kalp algorithm again. And I won't bother you with the numbers, but the numbers is just messy. I mean, they don't help anything. So this is Bellman-Held-Kalp algorithm, which just take the computation of all the subproblems, and I get n to the power of 2 times 2 to the power of n complexity, which is obviously also horrible. But with this algorithm, I could maybe do like 35, 40. I could maybe do a traveling salesman of 35, 40 nodes, which is awfully a lot better. So I'm telling you about dynamic programming now, and really, why should we care? We're just building websites. And I'll claim that if you're only building WordPress sites, or if you only do company presentations with the contact information, yeah, this is not really for you. But if you're doing something more cool, like if you want to show the best scored restaurant, or if you want to match people and companies like I'm doing, or if you want to somehow figure out the best score of a picture, or building recommendation engines, or whatever, graph theory is super interesting to look into. And the cool thing here, you don't really need to solve your problem. You only need to convert your problem to a graph theory problem, and the solution is pretty much there for you already. And dynamic programming is a way for you to make your algorithms more efficiently. So I hope I've given you some inspiration that shows that it's more to programming than just printing HTML, and I hope you enjoyed my talk. Do you have any questions? One question, front row.
Hi. Well, I got a little confused by your list of time complexities for the different graph search algorithms.
Yes?
Because you've listed, I think, the depth first, breadth first, and the Dijkstra algorithm as having the same complexity.
Yeah.
How does that work? Because the depth first and the breadth first are supposed to pretty much search the entire graph, whereas the Dijkstra pretty much, it doesn't.
Yes, that's an excellent question. I maybe missed explaining this. I'm going to go back to this image. I noticed it's a lot more images than I thought it would, but I'm dedicated now. No, sorry, I missed it. There's a short command. Anyhow, time complexity. I'm committed now, sorry. Here. This one?
Yes.
Yeah. Time complexity shows worst case scenarios. So in the absolutely worst case, we have a linear time complexity. And in Dijkstra's, we have an absolutely worst case scenario, we have n times n log n algorithm. But on the average case, we have a way better one. On Dijkstra's average is way better, but the other, they always search the full graph. So big O notation is the worst case. Did I answer?
Yeah, that answers the question. I have one other question.
Sure.
On your explanation of applying dynamic programming to Dijkstra's algorithm, it's not really clear to me how it helps in this case, because Dijkstra's algorithm already provides some sort of more efficient search, and you don't really look at the same stuff twice.
Dijkstra's algorithm is a dynamic programming algorithm.
Ah, right, okay.
Yeah, I wanted to show it in a graphical way how it actually is dynamic programming by reducing the number of squares.
All right, thank you.
You're welcome, thank you. Great questions. If you have any feedback on my talk, I mean, I've done this talk once before, and I will do it more in the future. I'll happy to include feedback like this in my talk next time. So please write it down and join in. I mean, if you liked it, give it 5 stars. If you didn't like it at all, I mean, it seems to work to give me 1 star. I don't know. But please give me some feedback. And thank you for listening.
Okay, Tobias, thank you. If there are no more questions, then we just have to take a short break, because Michael Column will start at 5 sharp in order to have closing ceremony on time. So see you back here in 20 minutes. Thank you.